Okay, good morning, everyone. So this is a tutorial problem for week 2. And so we have to do question by question. So this one, so the first question is about binary representation of numbers. And so you can see that there's two cases. One case is the number is bigger than 1, and the second case is the number less than 1. Okay, so how do we do that? So, so suppose I try to find the binary representation of 193. So let me share my document camera. So how do you find? Can you see? You can see it, right? So 193. So you can read it, right? So I can write a bit bigger, but 193 is, so how do you find 193? The binary representation. So you just keep dividing. So you make a table like this, keep divided by 2, yeah? So this is 193, so x, okay? And you take x, you modulo 2. So you take the x, you divide it by 2, and you check the remainder, okay? So 193, you divide it by 2, then you get 96, and you get the remainder is 1, okay? Then 96, you divide it by 2, you get a 0 remainder, and you get 48, okay? Then 48, you divide it by 2, then the remainder is 0, and you got 24, okay, and so on. So 24 remainder, when you divide by 2 is 0, and you got 12, okay, and 12 remainder is 0, and then you got 6, and 6 you have a bit out of focus. Can you see it now? I try to make it look sharper. Does it look better now? Okay, thank you. So now, so you have 6, yeah? So 6 you divided by 2, then you got remainder is 0, and you got 3, okay? And then when you divide it by 2, the remainder is 1, and 1.5, but then 1.5 you have to now up to 1, yeah? And then 1, you divide it by 2, you got 0, and the remainder is 1. So you stop here, okay? So now you just read the table from the right to the left. You read it back like this, okay? So you got 1, 1, then 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 zeros, yeah, and then 1. So this is a binary representation of 193. Well, you check whether it's correct or not. So remember, the first is corresponding to the 2 to the 0 power, right? So 2 to the 0 here, okay? And the second one is 1, 2, 3, 4, 5, 6. So this is 2 to the 6, yeah? And then this one is 7, so 2 to the 7. Okay, 2 to the 7 to the 6 plus 2 to the 0. So this one is, so 2 to the 6 is 64, 2 to the 7 is 128. So you got 128 plus 64 plus 1. Okay, and this one is 89, so 3. So 13, yeah, and then 2, 6, 8, so 9, so 193. Okay, so you can verify that your expansion is correct. Okay, so always check by verifying whether you got the correct expansion. Okay, so this one maybe you've seen it before. Okay, but now what happens if I have a number less than 1? Okay, so now how about the boundary expansion of 0.1? So you see, now we have to use a different algorithm. You know, you cannot divide this number by 2. It doesn't make sense. Okay, so now the algorithm is, so the position 1 is y. Yeah? So the algorithm is you multiply by 2. Okay, so now the algorithm is you draw a table. So y is here, and you check whether 2y is greater or equal 1 or not. So this is a logical value. It could be either 0 or 1. Yeah. And now, so now suppose I put in y equals 0.1. Okay. Then I take 2 multiplied by 0.1. Then I got 0.2. 0.2, is it bigger or equal 1? No, it's not. So I put 0 here. Okay. And then, okay, so I got 0.2. And remember, everything here is modulo 1. Modulo 1 is when that is bigger than 1, you have to take off 1. Okay. And now 0.2, you multiply by 2, then you got 0.4. So 0.4 is still not greater or equal 1, right? So it's still 0. So put 0 here. Then you multiply by 2, you got 0.4. Okay. And then now 0.4, you multiply by 2. Then you get 0.8. 0.8 still less than 1, so you got 0 here. Okay, but now you got 0.8. Now 0.8. If, sorry, what do you mean by modulo 1? It's a good question. I will show you right in this step. Modulo 1, it just means that, you know, if it's bigger than 1, then we have to take off 1. See, because you keep multiplying, right? Eventually it will be bigger than 1. Right? Then we have to take off 1. And that is modulo 1. So when you read the solution, then I will explain why you get this algorithm. But now we don't have time to explain the algorithm. Yeah. But now just do the algorithm first. Yeah. Okay. So now 0.8, you multiply by 2. Yes. Then you got 1.6. So 1.6 is bigger than 1. So you write 1 here. But 1.6, remember, you modulo 1, then it becomes 0.6. Okay, so you take off 1. And then 0.6, when you multiply by 1, sorry, multiply by 2, then you got 1.2. So 1.2 is bigger than 1. So you write 1 here. Okay, and then modulo 1, so you got only 0.2 here. Okay. And now 0.2, then you got 0, and you multiply by 0.4, you got 0. And, you know, I mean, if you make the next, the next calculation, then you got, sorry, you got, you multiply by 2, you got 0.8, right? 0.8, you multiply, so this one is y again, 2y greater equal 1. Then you got 1.6, so you got 0.6 here, you got 1 here, and you got 1 here. Then multiply by 2, you got 1.2, so it becomes 0.2 again. And you see the pattern, it got repeated. So 0.2, so 2, 0.2, 0.6, 0.8, then 0.6. Okay, so it's like one cycle. And then this one is another cycle, 0.2, 0.4, 0.8, 0.6. Okay, so another cycle. So just keep repeating. And see now the binary representation of 0.1 will be, now you have to read from the left to the right. Okay, it will be 0.1, 2, 3, 0. So 1, 2, 3, 0, and 1, 1, 0, 0, 1, 1. You see now, you see it will be infinite. Yeah, and you see that 0, 0, 1, 1 keep repeated. So this one keep repeated. So 0, 0, 1, 1. Okay, so you just keep repeated. You can draw another one, and so on. Okay, so this one is the binary representation of 0.1. I mean, this is a decimal. Okay, but this is a binary. Okay, so you see in this case you have infinite many digits after the dot, and 0.1 is is a very famous example for binary representation that has infinite many digits. So you see, for example, like pi, in decimal you have infinite many digits after the dot, 3.11, sorry, 3.1415, something like that. So the same here for the binary number, and you can check whether this is correct by maybe a similar example. Maybe let me take a similar example to see whether this is correct. Yeah. So now suppose you want to find binary representation of 0.375. Okay. So you write y here, 2y greater or equal 1. So now 0.375, right? So when you multiply by 2, yeah, it is still less than 1, right? So you write 1 here. So you write 0 here. So multiply by 2. This one gives you 75, 0.75. Yeah. Where is it? No. What I want is it correct? 375. 375 multiplied by so 375 multiplied by 2, right? So this one give you 0.5. Yeah, it's correct. So 0.75. Yeah. So then 0.75 when you multiply by 2, yes, then you get 1.5. So 1.5, then this one is bigger than 1. You write 1 here. So then this one you got 1.5, but you have modulo 1, so it becomes 0.5. Okay. So 0.5. Now you multiply by 2, right? You multiply by 2, that exactly equal 1. So right here, you just write 1 here, okay? And then, because you multiply by 2, you got 1, but you modulo 1, you minus 1, then you got 0, okay? So then 0. So this one, in this case, stop. It doesn't have infinite sequence. So now check, okay? So now my claim is decimal 0.375. In binary, it's just 0.011 in binary. Okay, so you put 0 here, doesn't make any difference. Okay, then check whether it's correct or not. So this one is power minus 1 minus 2. So this one is 1 over 2 to the 2 plus 1 over 2 to the 3. Okay, so because this one is power minus 1 minus 2 minus 3, yeah, and this one is 1 over 4 plus 1 over 8, so 0.25 plus 0.1 0.25. Okay. So then this one is 0.375. So it's correct. Okay. So that is the algorithm. How you get the binary representation of a number less than 1. Okay. So any question about this one? So when I post the solution, you will see the reason why I come up with this algorithm. Okay, so the reason just come from the way you expand the number in binary form. Okay. Okay, so the next one is, suppose I give you a binary number, then how do I recover in the decimal? So 1 0 0 1 1 0 1 1. Okay, in binary. So how do we get it in decimal? So remember the power. So the power here is 0 1 2 3 4. So 2 to the 4 plus 2 to the 1 plus 2 to the 0 plus. So now go beyond the dot. Yes, the power of 2. Yes. So this one is power minus 1. Yeah, this is power minus 2. So 1 over 2 to the 2. This one is power minus 3. So 1 over 2 to the 3. Okay. And then, this one is 16. One is 2. This one is 1. This one is 1 over 4. This one is 1 over 8. So you got 19 plus 0.25 plus 0.125 and 19.375. Okay, so this is a easy process. Yeah. Okay, so explain in MATLAB why we have real max equal this number and why real mean is this. On MATLAB, I try to do my bin to decimal. I think that is a very good question. So actually you have to use the correct form of the command. Yeah. So let me show you how to use it. So let me go to MATLAB and so my bin to decimal. So you have to, let me share my MATLAB. Yeah. So help my bin to decimal. So you have to give the string. Okay. So now suppose you give my bin to decimal, then you have to give a string like this. So 1 0 0 1 1 dot 0 1 1. There you see, then you got 19. Is the lab compulsory? No, the lab is not compulsory. The tooth is not compulsory. Nothing is compulsory. Okay. So only the assignment, the lab test, the project, and the final exams are compulsory. Okay, but the lab and tutorials are optional. Yeah. So now you see now, Helen, can you get it? Okay, so you have to put in the string. You have to put the quotes in the front and in the back of the string. Okay, so now go back to the next question. Yeah. So now why we have a real mean is this big value and that value. So I think I explained this one in the lectures already, but maybe do it again, just in case you haven't watched the lecture. So the real max, okay, is you take the floating point number and you turn on all the digits, okay, and you take the maximal power, E max, yeah. So in MATLAB, when the double precision, then Emax is just 1023. Okay. So then now how do you compute these values? Switch to MATLAB again. Okay, so I can switch to MATLAB again. Yes. Add powers up to, yes. This one, yeah. But so somebody asked me to switch to MATLAB. Yeah. So you see MATLAB. Okay. So now go back to the real min, real max. Yeah. Okay. So real max is now you use geometric series. Yeah. So 1 plus 1 half plus 1 to the 2 plus. So remember you have 52 digits. Okay. In the double precision. So 52 digits. So you have to add up to 2 to the 52 and you multiply by 2 to the 1033. So this one by the geometric series formula, so you got minus 1 over 2 to the 53, 1 minus 1 half, and 1023. Okay. And so this one is 2 to the minus 52, and then you multiply by 2 to the 1023. Okay. And this is a big number, so you cannot, well you cannot do it by hand, but suppose I put in MATLAB. So I put in MATLAB, then you if you put in MATLAB this number, then you get exactly real max. So I got 2. So I put 2 minus 2 to the minus 52, and I multiply with 2 to the power 1 to 23, and I got this number, and this number is exactly real max. Okay, so you see that. And then similarly for real mean, yeah, so real mean you just for real mean you just go back to the expansion and you turn off on the digits. Okay, you turn off on the digits, and so now, so this one is some number here. I don't want to copy that. So real mean is you turn off all the digits here to be 0. Okay, so 1 and 0, 0, all the digits here, and then you times e 2 to the e mean. Yeah, and this one is just 2 to the, so in this case e mean it just minus 1022, and you put in MATLAB, you will see that is about 2.251 e to the power minus 308. Okay. Okay, so now any question? Okay, so no more questions. So now we move on to the next question. Yeah. So the next question is, you have a program. Okay. So now you can see that the program, you can type it in MATLAB. Maybe let me type in MATLAB. Yeah. So, and then okay, so we make a new script and we say that n equals 6, m equal 2, k is in 16 n over m, and A is, now you set A to be a zero matrix, okay, n by n, and for I is 1 to m, then low is I minus 1 times k plus 1, and high is I multiplied by k, and then A low high is I once k, and then run it. So print out the matrix and print out number of zero of matrix. And now you can see that if I run it, but ask me to save as something like maybe put to, okay, something like that. So okay, if you see that, if you run the program, you see that the first iteration, it will make the block 1 1 1 here, 1 1 1 here, and 1 1 1 here. Okay, because if you set I equal 1, then low is just equal 1 and high equal you know, in this case it's just equal 3, yeah, because k equal 3, so 6/2 just equal 3. Okay, yeah, easier to cut and paste, yes, 2 lines, yes, thank you. So you see that now now if you change to n is 10,000 and m is 10, so how many gigabytes you need to store the matrix A? Well, so now go back to the question, yeah. So now suppose I want to start the matrix A, yeah, but I start the full matrix. So n is 10,000, m is 10. Okay, now I want to start the full matrix. So how many gigabytes do I need? So the number of bytes, okay, that to store the full matrix A, it's just 8 times n squared. Okay, so why is that? So n squared is the number of entries of the matrix. For each entry, yeah. So each entry, what is a real number, okay? And so you just put it in. So this one give you 8 times, you know, n squared is 10 to the 4 square. So what is 8, 10 to the 8 bytes? Okay. And if you want to convert it to gigabytes, okay, so 1 gigabyte is 2 to the 30 bytes. So there is 2 convention, okay? So one convention is 1 gigabyte is 2 to the 30 bytes, and another convention is 1 gigabyte is 1 billion bytes. Okay, so it depends on what convention you use. You just say it. Yeah, okay. So 1 gigabyte is 2 to the 30 bytes, yeah. So then you know, I mean, this one you just take 8 10 to the 8, you divide it by 2 to the 30, and then you with 10 Yeah, so you know, I mean this one, there is two convention. One is you use 2 to the 30, and this number is a bit more than 1 billion. Okay, and another convention that just use 1 gigabyte is 1 billion bytes. Yeah? So now if you take this number and then you put in the calculator or put in MATLAB, then what do you have? So you got 10 to the 8 divided by 2 to the 30. So you got about 0.75 gigabytes. Okay. But now the next question is say that, okay, now if you want to store only the non-zero entries. Okay, so now we have to go back to see what is the structure of the matrix. So what is the structure of the matrix? So now if you look back into the program, okay, you will see that now you will see that in the program, yeah, you have a for loops, okay, and it has I is the number of iterations that go through the blocks, the diagonal blocks like this, okay. It up with, you know, 1 1 1 1 here, 2 2 2 here, 3 3 3 here. Okay, so go back to low equal I minus 1 k plus 1 I equal I times k, right? And then A low high is just I times 1 k, right? So that is now, and just then what do you see? You see that I is 1, right? So suppose m equal 2, then I can run only from 1 to 2, right? So when I equal 1, then what is low? No, I'm still here, yeah. Sorry, yeah. So I try to say it a bit louder, yeah. So low. So in this case, you know, if I equal 1, then you see that I minus 1 equals 0, so give you 1. And high equal, so remember k is what? K is just n over m. So what is just 6 over 2 equal 3. Yeah. So in this case, then high is just equal 3. Okay. Then you have A13 is equal 1. So you see the matrix A look like this. So you got, you know, n by n, this is 6 by 6. So you got 1 2 3 1 2 3 here, 1 2 3 1 2 1 2 3 1 2 3 1 2 3 1 2 3 1. So essentially, you know, 1 to 3 is here. So you just make it 1. Okay, so this is the first block. Okay, and now so this one is a first iteration of the loops, yeah. And now you go back, you say that what happened when I equal 2. Okay, when I equal 2, then low is just equal. So you put it back here. So I equal 2, then 2 minus 1 is 1. Okay, so 1 multiplied by 3 is 3. 3 plus 1 is 4. So low is just 4. Okay, then height is 2 multiplied by 3 is just equal 6. Okay, so then this one A, so the assignment will become A 3 to 6, 3 to 6 is equal to 2. Okay, so that means that now 3 to 6 is here. So well, not 3, sorry, 4 to 6, yeah, because low is 4. 4 to 6, 4 to 6. Okay, so 4 is right here. So 4, 5, 6. You see, so 4, 5, 6. But then the column is 4, 5, 6 as well. So this one 4, 5, 6 is 2, 2, 2, 2, 2, 2, 2, 2, 2. So you see it now. It's set another blocks. Okay, so this is the case for M. It just equal 2. Okay, only 2 blocks. But in general, now you know M. Now M become M is in this question becomes 10. Okay, then you should have 10 blocks. Okay, so why we are doing this? Well, because we want to know how many non-zero entries, right? Because remember, everything else is just equal zeros, and only those blocks are the non-zero entries of the matrix. Yeah. Okay, so now go back to the case M equal 10. M equal 10, and N is 10,000. Okay, so now what is the structure of the matrix? So how many blocks do we have? So how many blocks? How many non-zero blocks do we have? How many blocks? How many blocks in this matrix? How many non-zero blocks are this? 10. Yes, so we have 10. So block 1, block 2, block 3, up to block 10. Okay. And now how many entries, how many non-zero entries in each block? So we have 10 blocks, yeah. And how many non-zero entries in each block? So what is the size of the block? 9 entries. Why 9 entries? Well, remember, before you have 9 entries, I agree, yes. But 9 entries here is for M equal 2 and N equal 6. Okay, so you take 6, you divide it by 2, and then you got 3 by 3 here. So then you got 9 entries. Yes, should be k square per blocks, yeah. But then k square, what is k? In this case, what is k square? Non-entries, non-zero entries per block, yeah. But what is k? Well, k is 1,000. Well, k, you know, if you look at the program, yeah, k is just n over m. Okay, so we just write in the general form. So k is just n over m. You look in the program, it defines k is just n over m. Okay, so in this case, then k is 1,000. I agree. Yeah. Well, you have to take. Okay, so now you have to take the number of blocks. Yeah. So the number of blocks. So the number of non-zero. So the number of non-zero of A is equal to the number of blocks multiplied by number of entries per block. Yeah. Remember, all the blocks here are non-zero. Yeah. So per block. And now we remember that the number of blocks is m, right? And the number of entries per block is just k square. So k square is n over m square. Yeah. And so now you got the number of non-zero elements is n square over m square multiplied by m. So n square over m. Okay. So that is the number of non-zero element. And now it's a very general. Now you can put in any n and any m. Okay. Yeah, it's good. So now let me put in. Okay. So remember the number of bytes. Yeah. To store sparse matrix A. Will be 8 multiplied by n squared over m. Okay, remember we have 8 bytes per entries. Yeah? So this one will be 8 multiplied by 10 to the 4 square over 10. Okay, so this one is easy. So this one we just put in, you know, you got 10 to the 8, 10 to the 7 bytes. Okay, and now you can you know, convert to gigabytes. Yeah, so in gigabytes you got 8 multiplied by 10 to the 7, you divide it by 2 to the 30, and it will be 0.075 gigabytes. So you see 10 times less than the full matrix. So if you start only the non-zero entries. Yeah. So in this problem, the tricky part is to just figure out the number of non-zero entries. Okay, but after that, just plug it in. So you know, but you have to work out what is the general formula for the number of non-zero entries. Okay. And now the next question is epsilon. Okay. So epsilon is epsilon n. So question sparse matrix only store the non-zeros. Now actually it store the indexes as well. But you know, I mean the number of indexes is of order n. Okay. So I store the non-zero entries and the indices of the non-zero entries. But it's still a lot, you know, less than if you store the full matrix. Okay. I mean, we just simplify by saying that, okay, we compute only the non-zero entries, but, you know, I mean, roughly you multiply that by 3, then you got the size of the sparse matrix, but it's still smaller than the full matrix. Okay, question number 4 is about epsilon. So epsilon n. So epsilon n is the gap between n and the next machine number. Okay, so what does it mean? So suppose I have, you know, like, well, we have epsilon without no input, it's just epsilon of 1. Okay, then you know that this is 1 and this is 1 plus epsilon, the machine number. Okay, and then if you write 1 plus, now I go back to the MATLAB. Yeah, so you see that now if I put in 1 plus epsilon bigger than 1, then it's 1. Yeah, but now suppose I put 8 plus epsilon, then what bigger than 8, then what do I get? I get 0. Yeah, so why is that? Well, because 8, the next machine number should be 8 plus epsilon of 8. Okay, then this is true. Okay, so you see now I want to explain. So what does it mean by epsilon of a number n? Okay, so we do some simple example. So now go back to the piece of paper. Yeah, so now suppose I take like epsilon of 2. So what is epsilon of 2? So remember 2, when you expand it in binary form, then it will be 1.000. So how many 0 here? 52 digits, 0, multiplied by 2 to the 1. Okay, so this is a floating point representation of number 2. And now 2 plus epsilon 2 will be, remember the on the meters of the car, you have finite many digits. You turn on the last digits. Okay, so this one become 0, 0, but the last digits become 1. Yeah. Okay. And then, this one gives you the difference between epsilon, 2 plus epsilon 2 and 2 is just epsilon 2. And we equal 2 to the minus 52 multiplied by 2 to the 1. It's just 2 to the minus 51. Okay. And maybe we do the same for 3. Yeah. So maybe epsilon of 3. So epsilon of 3, you have 3 is 1.1 and 0, 0, 0, 0, 52 digits here. Multiplied by 2 to the 1. Yeah. Remember this number 1.1, you multiply by 2, you got 1, 1 and 1, 1 in binary form, which is give you number 3. Okay. Then 3 plus epsilon 3 will be, you turn on the last digits. Okay, so 1 here. And so epsilon 3 is 2 to the minus 52 multiplied by 2 to the 1 is 2 to the minus 51. Yeah. Why does it happen if the last digits is already, what happened if the 52 digits is already 1? A very good question. So what happened if the last digit is already 1? Well, if the last digit is already 1, then I think you have to add it. So okay, so now maybe let's take another extreme example. Okay, so suppose the last digit is already equal 1. So what is, suppose I just take epsilon, what is the last digit is already equal 1, yeah? Okay, so this is epsilon, the binary representation of epsilon, yeah? So then what is the next digit right after epsilon? Well, you have to add on, right? Because now this one will be, so it will be the next digit will be, you have to add on 1 here. Yeah. Then this will become 0. So this one is 52 digits. Yeah. Okay. So then the next digit, the next number, the next number will be, now remember, you like the odometers, you turn this one to the next one will be 0. And then the next one will be, the 0 will become 1. Okay, so then this one will be your next machine number. So now this one will be, the 50, this is the 51st digits. Would you have epsilon of epsilon? It's a good question. Well, we can try it, but I think epsilon will just take in. That's a good question. Let me try it, see whether that works or not. So, but I believe that epsilon will equal 0 because it becomes so small, you know. So epsilon of epsilon, oh, no, it's not 0. Okay. So it's very good. So, well, but I think that the principle is the same. You have to get the binary representation. Yeah, so epsilon, you see, epsilon is the positive distance to the next larger of the same precision. Okay. So epsilon without any parameters is the same as epsilon of 1. Okay, but then otherwise you have to find the binary representation. Okay. Yeah. So there's a lot of example here. So maybe you just look it up. Okay, but essentially epsilon of epsilon is still okay, provided that you have to find the binary representation of epsilon, and then you just, you know, I mean, okay, have a good weekend. Yes. Okay, so now so you get the idea, right? So now let's see, we have time for another question. So the next question is about catastrophic cancellation. So okay, so now the next question is about catastrophic cancellation. So if you've done the lab, then you know, you have to solve the quadratic equation. Yeah, ax squared plus bx plus c equals 0. Okay, and x1 equal minus b plus square root b squared minus 4ac divided by 2a, and x2 is minus b minus b squared minus 4ac over 2a, right? And now you've seen it in the tutorial that if b positive, okay, if ac are very small, yeah, small, yeah, then x1 could have catastrophic cancellation. Catastrophic cancellation. Okay. And you see, because you see now AC very small, so this one is close to B, right? B squared, I think it's very close to B. Close to B, then you minus B, then it causes catastrophic cancellation. So you saw it in the lab, one of the question. Yeah. And now how do we fix it? Well, we fix the formula. We have to fix the formula. So there is no other way. We have to fix the formula. So B squared minus 4AC over 2A. And now you can make a equivalent formula by, you know, multiply by the conjugate of the square root. Yeah. So then you multiply by B plus, while you multiply and divide it by the same thing. Yeah. Okay. And you use the identity x squared minus y squared equal x minus y, x plus y. Okay. Then, you know, you can reduce this one to b squared minus, or maybe b squared minus 4ac. Yeah? So the whole thing minus b squared. Yeah, this one minus b squared and divided by 2a b plus square root b squared minus 4ac. Okay, so then b squared got cancelled, 2a, so you got minus 2c over b plus square root b squared minus 4ac. And this formula doesn't have catastrophic cancellation. Okay, so you can try to fix the lab. And you can do the same for the case x2. Okay, so I just leave it as an exercise. So any question about this? So that is number 5. And now number 7 is very similar. So suppose you have y equals square root of 1 plus x squared minus square root 1 minus x squared. Or maybe we do number 9. Yeah, number 9 is about big O notation and little O notation, and then we stop. So hopefully we still have time for one last question here. So now number 9. So suppose I want to show that square root n is a little o of n. Okay. So by definition, you take the limit of the ratio square root n over n. Yeah, and if this limit equals 0, then you say that square root n is a little o of n. Okay, so this one is the limit of 1 over square root n, and then this one is just equal 0. Okay, and you can do the same for, say, logarithm n. So logarithm n is another big O of, sorry, little o of n, because if you take limit of logarithm n over n and go to infinity, so this one you have infinity over infinity, so you got to take lots of the rules. Yeah, so lots of the rule give you 1 over n, and this one give you 1 and give you 0. So logarithm n is little o of n as well. Okay, and then there's a question about big O notation. So big O notation, for example, you have like n to the k plus n plus 1. Okay, so this one is a big O of n to the k. Okay, and why is that? Well, because you take n to the k plus n plus 1, then less than 3n to the k for all n, greater equal 1. Okay, so by definition, this sequence is bounded by a constant multiplied by n to the k. So therefore, it's a big O of n to the k. Okay. So I think we don't have time now. So I think I have to stop here. So any question? So I will stop the recording. So